Fiber optic cables, transmitting information at the speed of light through cables. Fiber optic cable operates through the principles of total internal reflection. As light pulses travel along a fiber, the physical properties of the fiber cause the light to stay in the fiber. When applied correctly, the light can travel for over 100 kilometers without amplification. This principle was first described in the 1840s by Swiss scientist Jean-Daniel Caledon, who was studying light at a time when its properties were poorly understood. The first use of light to transmit signals was by Alexander Graham Bell, who developed a light telephone called the photophone during the late 1800s. The photophone operated through the modulations of a beam of light, and its demonstration managed to transmit a voice signal over 200 meters. The concept was later abandoned due to technological limitations of the time. Fiber optics did not begin to see use in the communications industry until the end of the 20th century, when improvements in technology and materials made their implementation feasible. The first transatlantic fiber optic cable, TAT-8, was constructed in 1988 and could handle 40,000 simultaneous phone calls at its launch. Today, the backbone of most networks are fiber optic cables. Fiber optic cables offer many distinct advantages over their electrical competition. Electrical cables are prone to picking up interference from each other and other sources, such as electrical motors and electric lights. Fiber optic cables can send data at far higher rates than electrical transmission. Electrical transmissions are limited by a number of physical factors, such as feedback of the cables and the inherent interference from the environment on the cables. Fiber optic cables can cross much greater distances without the need for repeaters. Electrical transmissions are limited to a few hundred meters, while fiber optic cables can cross over 100 kilometers without the need for retransmission or amplification. Despite these advantages, the implementation of fiber optic cables is still rather slow in coming to the general public due to a few key shortcomings of the technology. Fiber optic cables cost significantly more to install in residential and business settings compared to their electrical competition. Due to the nature of the data transmission, the cables must stay within certain specifications to maintain data integrity. Bends must be within a certain safety margin, otherwise the light will escape the inside of the cable and data will be lost. This is a major disadvantage compared to electrical cables, which have very high tolerances to physical bending. Fiber optic cables are more prone to breaking if handled incorrectly. Any mishandling of the fiber optic cable can cause the inner core to break, severing the connection of the line. During installation, bending or excessive shock forces can cause the cables to lose their ability to transmit information. In comparison, electrical cables can handle much more stress, and some common electrical transmission cables, such as Cat5 and Cat6 cables, come with built-in safeguards, such as a Kevlar strip intertwined with the internal wires to prevent stretching. Electrical networks are already in place in many areas, so the cost of implementing a fiber optic cable is unnecessary. Fiber optic cables cost much more to implement already. The addition of having to dig up the already functioning electrical cables makes immediate fiber optic replacement unreasonably expensive. Despite these shortcomings, there is already a race for the implementation of fiber optics in more networks. Service providers already advertise the use of their fiber optic data services in many large cities. Service providers such as Comcast, Time Warner Cable, and Google Fiber. In the future, expect that fiber optic networks start to replace traditional electric networks because of their improved data rates, capacity, and reliability. Thank you.